Hello everyone, I'm glad to take part in this international conference to present my work titled Synthesis, Characterization and Optical Properties of Azo-based iron and ruthenium organometallic complexes. The work I'm presenting is structured follows: Introduction, synthesis of the iron and ruthenium organometallic complexes, characterization by microanalysis, UV visible spectroscopy, and NMR of hydrogen, phosphor, and carbon, and cyclic voltammetry. Analog studies, third and second harmonic generation, and with a cognition. The organometallic complexes are among the most studied materials in non-linear optics. Their optoelectronic properties are highly dependent on the metal d orbital occupation and energy levels, which can be easily modeled through the choice of the metal, its oxidation state, and the surrounding. Among these complexes, the family of alkynyl metal complexes that can be defined as carbon-rich transition metal complexes which have a nearly linear metal carbon-carbon R structure demonstrate particularly swivel characteristic for NLO studies due to an efficient electronic coupling between the metal and the distant group via the p-conjugate pathway. This electronic coupling now has the metal-to ligand charge transfer. We report herein the synthesis and fuel characterization of 4 new azo-based ruthenium and iron organometallic complexes. The nonlinear optical response of these complexes relate to metal acetylate complexes have been evaluated by means of second and third harmonic generation. The compound 1, a frictional derivative, was synthesized via the Sonogashira reaction. 3 ruthenium complexes, 2, 3, 4, have been prepared by 2 steps procedure reported in the literature. These new complexes were characterized by microanalysis and NMR spectroscopy of hydrogen, phosphor, and carbon. By UV visible, the product 1 shows a wide and strong absorption band between 390 and 520 nanometer due to superposed pi étoile and DD transition arising from the ferrocell, together with n pi star and pi star absorption bonds of the azobenzene chromophore. The UV visible spectra for the alkynyl metal complexes 2, 3 shows broad absorption band from 380 to 550 nanometer that would correspond to the superposition of both MLCT and the pi star absorption bands of the azobenzene chromophore. In order to gain insight into the electronic environment of the metal atom in the new alkynyl complexes, the electrochemical properties of these compounds were measured by means of cyclic voltammetry. After the preparation of the thin films, we used the corona pulling technique in order to orientate the chromophore at the thin layer surface. First, they were heated on a hot plate at selected pulling temperature of 100 degrees Celsius. The measurement of second harmonic generation and third harmonic generation of product 1, 2, 3, and 4 in PMMA films at the concentration of 100 micromole per gram were obtained by using the Maker fringe technique for S and P polarized fundamental beam. The film of complex 4 was found to exhibit higher second-order optical nonlinearity than the 3 other films. This result might be due to different polarity and hence different charge transfer from the metal to the pi-conjugated acetylate azobenzene system MLCT in complex 4 as compared with the other two ruthenium metal complexes. The complex 1 is characterized with a higher third order than 2, 3, and 4 due to more effective electronic delocalization, which is caused by charge transfer from the NN-dibutylامine and ferrochenil donor groups to the azo-accepting unit. These results indicate that the present organometallic complexes are valuable candidates for optoelectronic and photonic application. In conclusion, we have reported herein the synthesis and fuel characterization of 4 specific organometallic complexes, the UV visible absorption spectra as well as the cyclical voltammetry measurement indicated a different metal to ligand charge transfer MLCT. Thus, the second and third order nonlinear optical properties of these 4 organometallic complexes have been evaluated by means of second and third harmonic generation techniques. The values of the second order susceptibility of our 4 complex were found to be the highest for complex 4, while complex 1 showed the strongest third harmonic generation. The difference of obtained values of second and third non-linear susceptibilities is due to modification of the energy states and the introduction of a charge transfer state upon complexation, which are of a different nature with the 4 metal complexes. Thank you for your attention.